Okay, hey folks, welcome back. So a couple of announcements today. We've got homework 9 and project 5 are both due tonight. Hopefully that's not too much of a surprise because we warned you about it 2 weeks ago and we warned you about it last week, so try and get that in tonight. Homework 10 will be released soon, and then project 6 will be out later this week. We haven't exactly decided when yet. But the biggest announcement is that the course evaluations are live, so please fill these out. That is like the number one way that we get feedback about how we're doing and how we can improve the course. So if you liked the course and you want us to keep doing stuff like that in the future, please fill out the evaluations. If you didn't like the course and you think that we should be improving things left and right, please also fill out the evaluations so that we can get that information from you. So yeah, when you fill out the attendance code later, there will be a link in there, so you don't have to remember what this link is. It'll be there. But yeah, there it is. So please fill those out. We'll remind you again next week, but try to get to it this week. Okay, so today we're going to continue our discussion of reinforcement learning. We got into it a little bit last time with bandits, but today we're going to sort of give you like the full picture. These are like agents that exist in the world that learn about the world through experiences and learn what to do and what not to do based on whether things work out or they don't work out. So here we have an agent who's faced with a difficult choice. Would you like to get an electric shock or would you like to pick up the gem? And we got to figure out how to act appropriately in situations like these. Okay, so the basic idea is we're going to have an agent. We're going to put that agent into an environment. This is like the real world. Finally, our models are hitting the real world. About time. So here's an agent, and basically once we have this agent in the world, we're going to try to incentivize this agent to do the behaviors that we want them to do and not do the behaviors that we'd like them to avoid by giving them these sort of reinforcement signals, these sort of reward signals. These can be rewards, they can be punishments, but basically a rational agent, and we're all rational agents in this class, right? We maximize expected utilities. We should be trying to get as many positive rewards as possible and avoid as many negative rewards as possible. So that's the picture. If you run at a diagram, everybody likes diagrams, so imagine we've placed the agent into the world and now it exists in this feedback loop between it and its environment. So the agent is like a maximizer. That's why it's kind of got that pyramid-ish shape, trapezoid shape. So it's taking actions that hopefully maximize its expected utility, but what's its expected utility? Well, it takes an action. The environment is like a chance node, so this is like kind of why it's got that green circle, and then the environment decides what happens next, right? So if the agent takes some action and it like does its homework, then the environment responds and it says, you get a good grade. So the state of the world is influenced by the agent's actions, and the agent gets a reward telling it whether that was a good action or a bad action. And these rewards are very important. The rewards are not necessarily immediately caused by the previous action. I mean, like in some sense they are, but like you can kind of set yourself up for success in the future by taking actions that might not get immediate rewards, but that set you up for picking up future rewards. And so there's this important feedback loop where the actions that you take at this time step will set you up for future success. So we have to sort of trade off between immediate rewards and long-term rewards. And so now we've got this agent, they're getting feedback in the form of rewards. The utility is defined by this reward function, and then we have to learn to maximize those expected rewards. But the big difference between this and like Markov decision processes is that now we just have experiences in the world, right? Nobody's telling us here's what the transition function is, here's what the reward function is. We're really learning all of this stuff. We're just interacting with the actual world. Okay, so this is like kind of an old concept in AI. Arthur Samuel designed this like checkers playing program in like the 1950s. And it basically did a couple of things that we've already talked about in this class. It estimated the values of states. So this is like, do I think that this is a state that's going to lead to, like the light colored piece is winning or the dark colored piece is winning? And so that's like your sort of value function, your evaluation function. And then on top of that, he trained this program to play games against itself. And so it would then learn from experiences playing checkers against itself and trying to come up with better and better moves. And the sort of big milestone here is that, up to this point, people thought, okay, well, a program's never going to be able to do anything that it wasn't programmed to do. That's the whole point of a program, is you program it to do something. And so there was this question of like, could a program ever do something that it wasn't programmed to do, that it wasn't like, that was smarter than its programming. And in this case, it was like one of the first like publicized events of that nature. So like Arthur Samuel was like an okay checkers player, and this thing became like a pretty high quality like amateur checkers player, and like at that point it was better than its creator at playing checkers. So when your program is better than you at the game that you trained it to play, it wasn't learning how to do that from you, right? So now we have a program that can do something that its programmer couldn't do. And so that's like an early success of this concept of reinforcement learning. Yes, question.
Can you talk about how it's slightly different from like minimax, like not evaluating all states but only going to a certain extent? Is that similar or is that different?
Okay, so the question is maybe I'm not quite clear on what the question is. So you want to compare the what they're doing with checkers here versus like Expectimax or Minimax?
I remember like a lot of times we do games, we do Expectimax or Minimax.
Yeah. So we will use this sort of Expectimax analogy as we sort of go through this, and there is definitely a useful analogy there. When you do Expectimax, there are certain things that you need to know that in the reinforcement learning context, you just don't know those things. So in the case of games where we kind of know how the world works, we can write down the rules of the game pretty succinctly. We actually can do Expectimax and all of that works fine. But when you get into something like this, there is no necessarily like rules that you can write down for like how a robot will evolve in the environment. And so you end up needing to do something more sophisticated. But we'll get back to that a little bit later in the class and this distinction between the two. But yeah, so here's another fun example, right? So this is RoboCup. It's like the World Cup, except you can only play it with robots. And so they had these like robot dogs, these Sony Aibos, and this is in 2004. And when you get one of these robots, they're sort of like, they're kind of like designed, they're marketed as like toys, and so people get them for their kids and stuff. And they do an okay job of walking around. Like if you just get them like out of the box, let me see if I can turn the volume down here. Yeah, so if you just get them out of the box, they kind of slip a little bit, and they slowly make progress across the pitch. But they're wobbling all over the place. It's kind of like the head is like, looking at this, looking at that. It's not super easy for you to like run a perceptual system on top of this. And so what they did was they actually trained these reinforcement learning agents on top of this platform, and then and basically tried to get it to optimize the speed with which it would walk across the pitch, and also the stability of the head. And what you can see, sort of giving away the next slide here, is that after they've trained it with reinforcement learning, you get a much more stable gait, and it's about twice as fast as when you started. So this is reinforcement learning and using it for sort of like robotics control. So not just games. And I was excited to hear that this paper came out like this month. This is like a paper from DeepMind where they've got humanoid robots playing sort of a similar RoboCup now. So it's still 1v1. So there's one player on each side. But yeah, they're able to do this in like, it's pretty impressive what they're able to do. They started with a policy that could stand up and another policy that could like score goals. And then they like distilled that into a learning agent, and then slowly over time they were able to like get this thing to improve its behavior. And so there's lots of other details on it, but we'll skip those. There's also this example, which is a fun one. So this is, again, a Google DeepMind paper. This is like deep Q-learning. We'll get into Q-learning later in this class. This is like a neural network that takes Atari pixels, like the video game Atari screen, as its input, and then its output is like the little joystick controller button presses. And so it's like very similar to the interface that a human would have when they're playing a game like this. And it's able, from pixels, to learn to control the paddle in a way that ultimately will end up solving this game to sort of like beyond a human level. What's sort of more impressive about this system is not that it's able to do this, but that it's able to do this across a wide range of tasks using the same algorithm. So this was like one of the first times that reinforcement learning was like truly a general purpose algorithm. So you start to see this kind of like generality of intelligence that we're sort of looking for, that I alluded to in probably the first lecture. And so you can keep running this. This is like after 2 hours of play, and after another 2 hours of play, it learns this really interesting trick, which is that if you keep hitting the ball on the left side of the screen or either side of the screen, you can kind of tunnel your way through. And if any of you've played this before, you might know this, but if you tunnel through on one side, then the ball will just bounce around behind the bricks, and it'll do all the work for you. You don't have to actually like catch the ball anymore. So it learned how to do that. So that's like reinforcement learning can do quite a lot of cool things. It's also the main, it's one of the main pieces behind this idea of AlphaGo, which is the system that ultimately beat the human world champion at Go. And it's something that you will explore in your projects as well. So yeah, this is the sort of robot-esque thing that you're going to be controlling in the projects. It's a very fancy robot called the crawler, and it has sort of two joints here. There's like a shoulder joint and like an elbow joint, right? So here and here. And you have torques that you can apply to those two joints to sort of rotate the limbs around. And the objective here is for you to move the crawler sort of over to the right, ideally as fast as you can, right? And so you don't accumulate reward if you just sit there, but you want to try and figure out how to move these limbs so that you start moving to the right. So here's a demo of what that looks like for a learning agent. So to start out, it doesn't really know how to do anything. It just kind of flails, right? It's just like applying random torques to these different joints. You know, the thing moves up, it moves down, it sort of like smacks the ground, it moves forwards, it moves backwards. It's not doing a whole lot of useful work there. But there's some controls here, and in this demo, like, I won't tell you what the controls do, we'll get to that later, but if you just sort of speed up through the learning process and you like skip a bunch of steps ahead, eventually it starts like, yeah, here's the skipping part. Eventually it will start like learning from that experience, and it'll learn what to do with these limbs, and the reinforcement learning objective will build a policy that allows it to sort of move to the right. And so we're like the system designers. We gave it a reward function. The reward function says you get points for going to the right. We could change the reward function and, you know, take the negative of the reward function, and then it would sort of push itself back to the right or back to the left. But yeah, this is reinforcement learning. You'll play with it in Project 6, and it's pretty cool. Like it's finally a program that like puts an agent into the world and has that agent like learn what the world is and how to interact with it. And there's like very few assumptions at this point left. So yeah, exciting stuff. Okay, so the big picture is like kind of the same as like Markov decision processes. We got here a couple of weeks ago. So remember we had this like car racing example. We had cool, warm, and overheated as possible states of the car. And we had a couple of actions. We could go fast or we could go slow. And if we went fast and we were cool, then the car might warm up. And if we were already warm and we went fast, we'd overheat the car. So we had states and we had actions and transition functions and reward functions, etc. Well, the change now is that we're not going to have the transition function and we're not going to have the reward function. They're still there, but the agent doesn't know what they are. Okay? So how do you learn a policy when you don't know that information? And that's the question that we're going to try and answer now, right? So we don't know which states are good. We don't know what the actions do. we have to explore states and actions and kind of figure out how the world works from our experiences. And to do that, we're going to need to combine like almost all the pieces that we've been looking at for the last, at least the last several weeks, but even potentially going back further than that, in order to like get a good approach for solving this problem. Yes? If we don't know, right, so the question is if we don't know what the reward function is or what the objective is, like how do we set up this problem? Is that the question? Yeah, okay. So it's a good question, and we will still need to define that stuff. We will need to say, this is the transition function for my simulator, this is the reward function that I'd like to incentivize the agent with, but we're not going to tell the agent in advance, here's a big table with a bunch of probabilities in it, that's your transition function. Here's a big table with a bunch of reward values in it, that's your reward function. We're not going to give the agent that information. We're just going to tell it, you know, you're in state S, here are your actions, good luck. And then it'll take one of those actions and maybe it gets a reward, maybe it gets a minus a reward, and then it lands in another state. And now we say you're in state S prime, good luck, here are your actions, right? And so the agent's just like interacting with the world and that's all it sees. So it sees S, A, S prime, R, right? State, action, next state, reward. But it doesn't know like what's the shape of this big reward function that has all the states and actions in it. It doesn't know what are the transition dynamics connecting all these states together. Yeah, I should probably be a bit more precise. Yeah, so the agent knows what the set of possible states is. It knows S in this big capital S set. It knows the actions. It does not know the transition dynamics or the reward function, but we might know those things. We're just saying like, we design a reward function that says we want the agent to go to the right. And so at every time step, the agent takes an action and then it gets to a particular state. We can run that state through our reward function to tell the agent what reward it receives. Okay? Yeah, other questions about this? It's kind of an interesting concept. Now the agent doesn't know this stuff. Okay? Yeah, so it gets complicated quickly. So if the MDP is unknown, lots of things change, right? Now we have to be thinking about exploration. If we don't know what the actions do, and we don't know what states we can get to, we have to try out unknown actions to see if they bring us to new states. We have to try and figure out, how does this world work? How do we get information? We have to explore. And then we also have to eventually exploit because we're expected utility maximizers, and that's what expected utility maximizers do. So eventually we have to make use of whatever we find out. We explore the world, but we want to sort of like get good rewards along the way. So there's the same tension that we saw in the bandits lectures of exploration versus exploitation. And we can similarly talk about like regret. So early on, you might have to take these exploratory actions. You sort of make mistakes, and then you lose reward in order to learn how the world works. And then over time, you'll try to make fewer and fewer mistakes. They're not really mistakes in the sense that, like, given what you know, it's perfectly reasonable to try a particular action. You might fall into a flaming pit of fire like we did in that grid world, but like, it would be reasonable to try that action knowing nothing about what happens. So it's not really mistakes, but it's like you could have done better, and later you'll learn that you could have done better, and so that's sort of where the regret comes in. And similarly, because things are noisy and stochastic and we're uncertain about what state we're going to end up in, there is this idea that we're going to need some sampling, right? It might take us multiple samples, many samples, in fact, before we're sure that we have a good estimate of how the world works. And similarly, we're going to need to try to generalize. So what we learn in one state, it might be useful for what we learn in another state. Maybe one action is always better than another action, and so we don't need to we don't need to try that second action in other states. Maybe that would be a useful generalization we could make. So all of these sort of these additional complexities get added to the picture once we have this initially unknown MDP situation. Okay, So we talked about bandits last time. We talked about MDPs this time. There is actually kind of a connection between these two concepts. Maybe this has occurred to you, maybe it hasn't. It's a little subtle, but when you're in a bandit problem, remember, a bandit is just like a problem model, the same as like an MDP is a problem model or a search problem is a problem model. So when you're in a bandit problem, really you can think of this as an MDP that has one state. It's exactly one state. And the state is you're standing in front of these two bandits and you're trying to decide which arm to pull. Okay? So that's like the big difference between bandits and MDPs. So bandits are just MDPs with a single state. You have the same set of actions in every state because there's only one state, and it's the set of actions, A. The only real difference with bandits to MDPs is that in bandits we have this stochastic reward function. So you pull an arm and it might give you a good reward, or it might give you, a bad reward. It might give you the same reward every time, but it could be stochastic in a bandit. In an MDP, we typically assume that the rewards are fixed, that they're deterministic, given a state action, next state transition. But that's like the main difference is this concept that there's only exactly one state for bandits. Then towards the end of last time, we started to generalize this to the idea of like a contextual bandit. And this is essentially an MDP where, okay, you do have the full state space, there's all these different states, but the transitions always return you to the start state distribution. So the transition dynamics from every single state just bring you back to the same distribution over starting states. So if you prefer to think about MDPs and you don't like bandits as much, then like this is a fine way of thinking about things, but you should just keep in mind that in a bandit setting, you might have stochastic rewards, whereas in an MDP setting, you're typically going to assume that there's deterministic rewards. Again, this is like, we get to put our modeling hat on from time to time and we decide, is this the right model for my problem? Do I want to think about it as a bandit or a contextual bandit or an MDP? And you could even say, okay, I'm gonna think about it as an MDP that also has stochastic rewards. That's just another type of problem model you could pick. But yeah, so these are sort of helpful and valid connections between bandits and MDPs. Questions on that? Okay. I also want to contrast offline versus online. So in the original setting when we introduced MDPs, this is sort of like planning. Like you have a model of the world, you just want to come up with the best policy. And so that kind of looks like this. You're in this sort of risky situation where you're on this bridge over the fire, and you want to figure out what your best policy is, but you have this model of the world in your head. You can test things out, you can try them, you can imagine what would happen. You think about what it would be like to jump off into the fire, and you say, if I do that, I'll probably land in the fire, and I'll probably incur the penalties that come with landing in the fire. So maybe I shouldn't do that, maybe I should, I don't know, depends on the penalties. You can contrast that with online learning, where you don't have this model in your head. You don't even know what the world does when you jump off into the fire. So what do? Well, there's only one way to find out. You have to jump off into the fire, right? So this is the learning case. So the planning side, you have a model of the world. You can make a plan. You can imagine possible futures, see if any of them are good. In the learning case, you got to figure out from experiences how to interact with this world. And it could be a little bit riskier because you might have to jump into the pit of fire. Okay, so there's a few approaches that we can take to doing reinforcement learning. The first and the most natural is, well, we have these nice algorithms, value iteration, policy iteration, that can handle when we have a model in an MDP. So why don't we just learn a model of this MDP, figure out what the right model is, and then solve that, and we'll get our policy, sort of the usual way. So all we would have to do is like take the stuff that we learned in the machine learning lectures, try and estimate the parameters of this model, and then use the model to do value iteration or policy iteration, and then execute the solution that we come up with. So that's the model-based approach. That's where we'll start. And then there's a few other approaches that say, when we can't learn a model, when that's too computationally difficult, or when there's other reasons, which we'll get into, that you don't want to learn a model, there's other things you can do. Like, you can estimate the values of states in this like kind of expecting max tree search. Maybe there's a way of still doing that value estimation, learning the values of these experiences when we don't have a model. Maybe there's still something that we can do there. And so we'll look at a few different approaches for that. And then we'll sort of look, probably we won't have time for this class, but we can look at it next time, is optimizing the policy directly. So this is more of like a hill climbing approach. So we have some policy, we want to change the policy so that it starts to get more expected utility. And so we could see like how would we go about doing that. Okay, so there's lots of different types of reinforcement learning, and there's two more that I will sort of draw your attention to: passive versus active learning. So passive learning is like there's a policy already. You can think of this as like policy evaluation in the MDP setting, where there's already a policy, we just want to know how does it do. And so we don't have control over what the actions that are being experienced by the agent, what those are going to be, because there's a fixed policy. And we're essentially watching as we play back the experiences that policy generated on like this projector, right? So maybe the agent jumps off and incurs a negative reward, and we're just sort of marking that down. We see that this is the experience that it was generating. We don't have any control over what it decides to do. That's the passive side. And then on the active side, we are the agent that's experiencing the world. We get to change our behavior after one of these experiences. And so there's like modification of the policy is like inside of the training loop. So we're generating some experiences, we then change our behavior, and then we generate some new experiences with our new behavior. So that's passive versus active. We'll start with model-based RL, and then we'll get into passive, and then we'll get into active, okay? So model-based RL will be the first thing. Today's code is projector. And remember, when you get to the thank you for filling out this form page, you should see the link to submit the course evaluations. So just keep that up, and then it's easy for you to get to it later. So yeah, model-based RL, the idea is we know how to solve MDPs. We already did that. How do we solve MDPs when we don't know what the MDPs are? Well, we could just try and learn the transition model. We'd try and learn the reward function. And then if we put those pieces together, what we have is an MDP. So we can just solve it the usual way. So that's the basic idea with model-based RL, right? We have some environment. We don't know its transition function or its reward function. We assume that they exist. And so we need to sort of like estimate this model based on our experiences, and then solve for the values, assuming that this model of the world that we come up with is correct. It's not going to be correct. You would need sort of an infinite amount of data for it to be correct. But hopefully if it's close enough, then we can still get a pretty good policy coming out of this. Okay, so we're gonna learn an empirical MDP model. It's gonna be maybe a crude approximation of the real world. And how are we going to do that? We're just going to do the same thing that we always do. We love counting in this class. We're just going to count some more. So we count up all the things that happen. We divide by all the times that we had experiences, and then we're going to estimate these transition probabilities by counting. Every time we see a transition, we're going to get a reward so each SA, S prime, each state action, next state is going to have a reward associated with it. And because we're sort of assuming that we're in the MDP land, we have deterministic rewards. So every time we see a transition, that's the only reward that we could possibly receive for that transition. So we just write down the reward and we move on. So this is how we're going to estimate R. We'll see an example of this in a second. But once we have this empirical model, we have this hopefully not so crude approximation to real life. We can then use that to solve the MDP. And that should give us a policy that we can try and execute, and hopefully it's a pretty good policy. Okay, questions on the approach before we do an example? Okay, let's do an example. Right, so here's a 5-state MDP. We've got states A, B, C, D, E. And yeah, so first things first, we want to do model-based reinforcement learning, right? So what we should do is we should generate some experiences. Let's suppose that we have some input policy pi, and that's going to allow us to generate these experiences. So we observe some episodes, right? Let's say that A and D are terminal states, and so that the policy eventually gets us to these terminal states. We have these 3-step episodes. There's one, episode 1 looks like B. We start at B, and then we go east, and then we get to C, and then we go east again, and we get to D. Okay? And the rewards along the way are -1, then -1, then +10. So +10 for exiting from D. Okay? And we've got a couple other episodes, and so these will constitute our training data. And just like in the machine learning unit, we can now like try and use this data to learn the parameters of our model. So what do we want in our model? What do we want in our world model? Well, we want a transition function, and we want a reward function. So let's start with the transition function. Oops. Trying not to give it away here. Okay. Ignore what you just saw. So here's the transition function. It goes from S to A to S prime, right? And what's going to be inside of this transition function? Like, how many entries are there going to be for starters? There's 5 states. Let's say that there's 5 actions. We can go north, south, east, west, and exit. So how many entries should be in this table? There's a probability for each transition. Yeah, raise your hand when you think you have an answer here. How many? Okay. Yeah. Do you know? Yeah. Say again? 25. Well, we need to have a probability for each of the possible next states. So that would be 5. Wait, I'm writing on my laptop screen. So we have 5. And then we have 5 actions. So you need to multiply those. But then there's another 5, because there's 5 states that we could start in also. So this is a probability for each of the next states for each of the state action pairs we could have started in, right? So this is like A, just to do one, A goes sort of east and then ends up at A. A goes east, ends up at B, right? ... A goes south, ends up at, I don't know, E. Then there's B, right? We have to do this for all the starting states, for all the actions, for all the next states. Okay, so yeah, let's just skip forwards to what this will look like, and I'll clear it out. So according to the slide, and we should verify this, the probability of being in state B, going east, and ending up in state C is 100%. Well, where did we get that from? This one here, B, east, C. All right, well, let's just look for B, east, C. We're counting things. That's like the way we operate when we're doing parameter estimation. So here's a B, east, C. Here's another B, east, C. Are there any more? Did I miss any? I don't think so. Okay, so this is saying, are there any other B, easts even? So this is saying all of the B, east pairs end up in C. So 100% is like totally reasonable for that to be what we estimate. Maybe it is 100%, maybe it's not. Maybe we don't have enough data to be sure. We only have 4 episodes. But for what we have seen, 100% is totally a reasonable guess as to what this transition probability is. Maybe you're thinking ahead and you're like, well, maybe we should do some Laplace smoothing on that because, you know, it's possible that there's like other things that could have happened. Maybe that's a good idea. For now, we're just going to leave it like this, but yeah, you could imagine adding some Laplace smoothing. So, okay, now what's the probability here? C goes east to D. All right, well, there's lots of potential C easts. So let me, I'll use a different color, right? We'll use blue for this. Here's a C east, here's a C east. There's a C east in every episode, okay? And how many of them wind up in D? Well, this one does, and this one does. This one winds up in A. Okay, so that doesn't count. So 3 out of 4, right? So we're counting these things. We say, all right, there's 4 total episodes. 3 of them wind up going to D every time we do east from C. So that's where this 0.75 comes from. And so that also makes sense. So these probabilities, we can just estimate them by counting the things that happen and putting the parameters into our transition matrix. Yeah? Say again? C goes east and ends in A. Yeah, so the next one, it's saying C goes east and ends in A. Well, so like just like we had in our grid world before, sometimes we slip, right? Sometimes we're, on that ledge above the fire and we try and go north and we fall east into the fire. Like that's the same sort of dynamics going on here. So yeah, sometimes we slip. Was there a question over here?
It was the same question.
Okay. Yeah. Another question?
Yeah, so is the matrix, is this a 125 by 1 vector?
A 120. So what's the shape of this matrix? Yeah, so it depends on how you want to format it. You can think of it as a 125 by 1 vector of probabilities, or you can think of it as a 5 by 5 by 5 matrix, sort of, or tensor, I guess. And yeah, whatever you prefer, it's fine. You can think about it that way. Yeah, in this case, I guess we're doing it as a vector. What other questions do folks have about this? Yeah.
We don't care about the reward yet, right?
We haven't done the reward yet. We'll do that in a sec. Yeah, right. So, okay, so a lot of people have this question, right? So we're in C, we go east, and then for whatever reason, this episode here says you actually wind up in A. It doesn't make sense. Like, how did we wind up in A? And just like when we were in the grid world before, let me see if I have a picture of that grid world somewhere. Yeah, remember this grid world? Right, we're in this grid world. Like when we're in this state here, sometimes we move north and we actually fall into the fire. Remember, there's like that slip probability. There's a chance. Like our actions are stochastic. We don't always go where we intend to go. We might slip and fall into the pit. We might slip and bump into the wall. So in the same sense that like our actions are stochastic, we might not go where we intend to go. That's all that's happening in this example. Does that make sense? If it doesn't make sense, please stop me and we can keep going. More depth. Okay, cool. All right, let me get back to where we were. So yeah, we're here. All right, great. So we've done the transition dynamics. Now we should do the rewards. Yeah, question?
You have to take into account the probability of slipping each time, I guess? Because if you can slip there, you slip anywhere.
Yeah, so why aren't we taking into account, like if we know the slip probability is 0.1, why aren't we taking this slip probability into account when we're accumulating these experiences? Well, we don't know the slip probability. That's part of the transition dynamics. That's the thing we are trying to estimate. So we can't use facts about the world that we haven't discovered yet. We have to just accumulate some data. Maybe we find that 25% of the time we end up in A when we go east from C, and we say, okay, well, that's just something that can happen in this world. Does it happen 1/4 of the time? Exactly? I don't know. Maybe we don't have enough data. We might need to get some more episodes and see, is it really as high as 1/4 of the time, or is it more like 1/10 of the time and we just needed some more episodes? But yeah, we're trying to estimate slip probabilities from data while we estimate sort of like how these, how do walls work? How do pits of fire work? We're trying to figure out all that stuff just by interacting with the world. Okay? All right, should we go on to the rewards? All right, let's do the rewards. So first, how many reward entries should there be? Our reward function is defined like this, R of S, A, S prime. We said that there were 125 entries in the transition function. It's the same number, right? There should be 125 entries in this one. And what will they be? Well, we have to find out. But essentially, every time we see a transition, we can write down its reward because we know that the reward function in an MDP is deterministic. So we see E goes north to C, right? And I can even put that in another color. Let's do purple now, right? E goes north to C. So then we go over to our reward function. We say E goes north to C. And what is the reward? It's a -1. Okay, so we put that in there. Now we have a reward function. We have an entry for E goes north to C. It's -1. Then we have another entry that's like A, exit, and I don't know, X. That's this entry here. There's like no next state because it's a terminal state. And that gets us a minus 10, right? So that's our reward function there. And we can go through and we can erase some of this stuff and make room. Okay, there's our reward function, right? So we can fill these things in. So that's where these numbers would come from. And I didn't actually do any of the ones on the slide, but you can see where these would come from, right? So you look at these transitions and then you fill them into the reward table. Yeah.
Is the reward always deterministic, or should we use stochastic?
So it depends. I mean, it depends on your environment. It depends on how you want to model it. The way that we're modeling this particular type of MDP, we're going to say that it's deterministic. But remember, in the bandits lecture, it was stochastic, right? You had to try an arm a couple of times before you could start to get a sense of whether it was good or not. So it depends how you want to model it. One way of thinking about this is that these are actually, we're modeling like expected rewards, and that you just always get the expectation. Yeah, I mean, you can decide whether you think that's a reasonable assumption or not, but for now, we'll just stick with that. Makes things a little easier. Okay, so we fill in our transition model. We estimate those parameters from data, very just like classic machine learning thing. And then we fill in our reward function, and we're just really writing down the rewards that we saw. Very easy parameter estimation when you just write things down. And that's it. We have our learned model, right? We have T, we have R. So what do? We use T and R, we solve the MDP, we get our policy, and we're good to go. So one benefit of this is that it makes really efficient use of experiences, because you have this model in your head, you can query it to see what's going to happen in various scenarios, and that allows you to generate data. So you only have to interact with the actual world to get your model, and then once you have a good model, you can learn with that model by just imagining experiences. And provided that your model is good enough, imagining those experiences is kind of like being in the real world. It's kind of like you're preparing for, you're simulating what's going to happen in advance, so that when you, let's say you're designing a rocket, you build a simulation of that rocket. The rocket, you learn how to get it to work in simulation, and then when you put it in the real world, you don't need as many failed launch attempts because you were trying stuff out in your head in your simulator before you launch the rocket. So you can make really efficient use of your experiences this way. But a couple of drawbacks with it. One is that it requires solving this MDP as sort of like a step in order to get this policy. And if we're playing Go, for example, the size of the state space is like 10 to the 170 states. Well, remember that like when we solve an MDP, it was polynomial in the size of the state space. I think it was like s squared times a. Does that sound familiar? So if it's s squared, that's 10 to the 170 states squared times the number of actions, which is like around 400 for Go. So you're not going to be able to tractably solve the MDP, even if you could figure out what it was. And furthermore, you're not going to be able to try every action in every state in order to build your transition model in the first place, and certainly not try it several times to see if you can figure out what the stochasticity is. Like, this is just kind of hopeless. We're going to need to figure out a better system than this. Okay, other problems with model-based RL. I like model-based RL. It's like a very intuitive approach, and I think that in general it could work, but if you solve some of these problems. But there's also this feedback loop. Right? We showed the agent exists in relationship to this environment, takes an action, the environment responds, we get a state back, and then like there's this reward. That feedback loop, where our actions affect our future states, which affects our future actions, which affects our future states, that tends to magnify small model errors. So if your model's off by a little bit, then when you sort of propagate forwards in your head, you're like, what's the next state going to be? You sample a state, maybe this is the next state. Okay, here's my S prime estimate, but it's off by a little bit because my model has these small errors. Okay, and then if I want to say, okay, well, what's the next state? Well, I could feed that estimated next state into my model. My model still has these small errors, so the next prediction would be off by some amount, just by the fact that the model has these small errors. But I'm now feeding in an input that's wrong. So the input is slightly off and the model is slightly off, and so these errors will compound. The further into the future we try and predict, the RL feedback loop is going to magnify these small model errors, and we're going to get this compounding error problem. Okay, and then a third potential drawback is that we're doing all this work to try and estimate our transition function. Transition function says, when I'm in a state and I take an action, what's the next state? And this is all well and good because we have this Markov decision process where states are Markov and they're a sufficient statistic for doing all this prediction. But how does the real world work? Does it tell you the entire state of the universe right before you take every action? Like, you all don't know what I had for breakfast this morning, and maybe that's not super useful information for your decision-making process, but you could imagine that you're a company and you're trying to, market to people a new breakfast cereal, and you kind of want to know what all of them had for breakfast this morning. You cannot know what all of those people had for breakfast this morning. It's just like, you can sample it, you can, make a sort of a popular opinion poll, you can ask people on the street what did they have for breakfast, but like, you're not going to get the entire state of the universe when you're ready to make your decision. So the environment is partially observable. Sometimes it's unobservable. And the idea that when you observe the entire state of the world is definitely like, now we have our modeling hat on. We're the model designer. We've like made a modeling error if we assume that we have full observability of the state. So when the environment is partially observable and we want to estimate this state transition function, but we don't know the state, how are we going to do that? So there's some other problems. Like this model-based RL, it works well for certain problems, but when we have some of these more complex situations, we might need to do something else. Okay? So this kind of motivates the idea of, well, what if there was a way to do reinforcement learning with a model-free method? We don't need to learn a model necessarily first. And the way that we're going to try to do that is to notice something about expectations. So what's an expectation? It's a weighted average of the outcomes according to their probabilities, right? So we can skip all of this other stuff on the slide and just think about an example. Imagine that I'm trying to estimate the expected age of CS188 students. And let's suppose, for the sake of argument, that I have a model of the age distribution for students, right? I know P of A, where A is the age. A is a random variable, but I know P of A. I have some model that tells me with these probabilities, maybe 35% of the time, students are 20 years old, and so on. Then I can just add together all the different ages and multiply by their probabilities, and that will give me the expectation. I can solve for it. Okay, so if I have a model, I can do this. Well, if I don't have a model, I'm going to have to collect samples, right? So I'm going to have to ask some people how old they are. I'll write down what they say, and I'll collect these samples. Maybe I get n samples. And what do I do with those n samples? Well, if I had a model, I could do this, but I don't have a model. So one option, and this is the model-based approach, is we could learn a model. We could try and estimate P of A, right? So we do our whole counting thing again. We say, well, how many times did someone answer that they're 20 years old, and how many people did I ask? And then I can estimate P of A, and we'll call that P hat. That's our estimate. Once I get P hat, I can do the same thing as in the green box. I can say, all right, I have my model. All I have to do is calculate the expectation, multiply every age by the probability that that age occurs, and now I have my expectation. This might feel like kind of unnatural. This is like not how we take averages usually. Usually we have, n different people answer our survey and they tell us how old they are. Well, what do? We just add them up and divide by n, right? We take the sample mean. So this might feel like kind of a not important distinction, but one of these is like a model-based approach, and one of these is a model-free approach. And they're subtly different. On the left, we're saying I first have to learn a model, this P of A, and once I have that, I can use that model to compute in closed form the expectation. On the right, we say, I have n samples. I'm just going to estimate from the data directly, and don't bother with learning the probabilities, because the samples are going to come in with the probabilities that they need to come in with, right? Like, I'm going to sample the more frequent ages more often in my sample. And so this one on the left, this works because over time, as we get more and more samples, we're going to learn a better and better estimate of the model. Our p hat is going to approach the true p. But this one, it doesn't sort of re-weight by this likelihood that something's going to occur. Like, why is this going to work? Well, it's going to work because we're going to sample things more frequently if they're more likely, right? The samples appear with the correct frequencies. Yes? Say that again? Yeah, okay, great. So how do we estimate the expectation? So there's, again, I'm presenting you with two different ways that we could estimate the expectation. One is like when we have the probability distribution, we can estimate you can think of the one on the left as like we have like an expectimax search, right? So we can, let me draw it this way, right? So we have some chance node, and then there's like a bunch of different outcomes. Let's say that there's the number of ages outcomes, and each one of these is going to have some value. So we can put the value in these little squares. And what we're going to do is there's a probability of age 1. And we're going to multiply that by the value that goes in here. Maybe that's like 18. Okay, maybe someone's 18. Maybe you're 18 with probability, I don't know, 0.19. Okay? And then we already said that there's another probability. This is like the probability that you're 20. So then probability of being 20 is, we said that was 0.35. That was down here. Right? So what we do is we just multiply the probability of an age by the value of the age, and that gives us the expected age. Right? So when we have this probability distribution, we can just do that. It's the same sort of like expectimax search thing. We take our chance node, we look at all the outcomes, we multiply the value of the outcome by the probability of the outcome. Okay? But again, this should feel a little unnatural because we have this sample, we have like, n different people. We asked them on the street, what's your age? And they told us, I don't know, maybe they told us 20, and then they told us 19, and then they told us 20, and then they told us 20, and then they told us 21, 18, 19. Okay, right? So we have a bunch of sampled ages. And what are we seeing? We're seeing, well, there's 3 20s, so 20 is more likely than 18. Okay, and then there's a 21, but 19 is more likely than 21. Okay, so we're starting to see some relative frequencies of these different things. If we just add up all those numbers and we divide by the number of people we asked, we're going to get another estimate of this mean. It's like the sample mean. It's like the sort of intuitive thing you would do. If someone said, what's the average age? You would say, well, let's ask a bunch of people and take the average, right? So that's another approach. And because these samples are sort of like all generated from that same underlying probability distribution, we don't need to multiply by the probabilities because we're going to get the samples with the probabilities they need to have. Okay? Does that distinction make sense? Yeah. Great. Other questions about this? Yeah. Totally, yeah. So the question is, why are we making this distinction? They feel like exactly the same thing. So I hear you, and I think that will probably become clearer once we show how it works in an MDP. Yeah, for now, just recognize that either we could learn the model and then use the model to estimate this expectation, or we could abandon learning the model and just try and do this sort of frequency-based summation sample thing. And like that's another approach, and we see that these are going to give us the same answer. I guess I haven't proved that to you, but you can trust me. If they give us the same answer, then we should be able to do either one, and this one doesn't involve modeling, whereas this one does. So let's see if we can use that to our advantage. Okay? All right. So we'll start with this idea of passive reinforcement learning because it simplifies things a little bit. We're going to assume we have a fixed policy, and we want to do policy evaluation, right? We want to learn the state values. These are our v pi of s values given our current policy. So we don't know t and we don't know r. Well, normally what we would do is we would do the sort of like expectimax search, right? Or we could even do like the sort of policy evaluation that we looked at in the MDP stuff. But all that required knowing t and it required knowing r. So how are we going to do this? Well, one way is to just directly sum up how much expected return we get, the expected discounted rewards from every state. So we're going to gather a bunch of data, and then we're going to try stuff out in the environment. Sometimes that will lead to doom, but we're just going to average across multiple trials and see what the average return is, right? Our average expected utility. So we take some policy, we put it into our 5-state grid world, and we observe some episodes using that policy, right? Here's episode 1, here's episode 2, episode 3, episode 4. And we want to estimate these values. So we want to build a value function, and a value function looks like this, v of s. So how many entries will there be in v of s if we have 5 states? We need 1 entry for every state, so we should have 5 entries, right? So there should be a v for A, B, C, D, and E. Okay? Well, let me write them as this, and we can put them in sort of like their grid shape. Well, what's the value? Let's start with B. So the approach here, where we're just estimating directly from data, the approach here is we're just going to look at all the episodes that include B, right? Here's an episode that has a B. Here's an episode that has a B. And we're going to look at all the trajectories. This is like sequences of experiences starting from B, right? So there's B goes to C goes to D, and we get a -1 plus 10. That's this one here. And then this one's actually the exact same experience. So we have the same experience again, -1 plus 10. So the value of B, if I've done everything correctly, should be +8. Just average together all the stuff we ever saw for B. All right, let's do it with another one. Let's do E. We'll do it another color. Yeah, here's a good color. So here's an episode that has an E in it, and here's an episode that has an E in it. Okay, well, what happens? First, E goes north, and we get a -1. And then C goes east, and it goes to D, and we get another -1, and then we get a +10 for being in D. So this one gives us a +8. And then we have another one that goes E north to C. I'll draw this in orange. Okay, we go north to C, we get a -1. We go east, and it does this weird sort of reroute, like we slip and fall, and we go to A instead. And then that gives us a -1. And then we get a -10 for leaving from A. So this one gives us a -12. Did I do that right? -1, -1, -10. Yeah. Okay. So 8 and -12, that comes out to plus, did I do that right? Yeah. So this comes out to be -2, -4, -2. Okay, so great. We could do this for the other states. Let's just sort of fill in the table. Is this making sense? Do you want me to do one more? Not making sense.
I don't know where the -2 is from.
Okay, so yeah, so the -2 is saying we need a +8 and a -12, and we're taking the average of all the rewards that we ever saw. These are all the sort of total expected discounted rewards. Here there's no discounting, gamma equals 1. So we're just saying, all right, here's a bunch of experiences, a bunch of trajectories that all started from state E. we're going to see what's the expected discounted reward that I'm going to see for those trajectories starting from E. And I get a +8 on one, and I get a -12 on the other. And so I'm averaging those things together. And if I did them right, we have to say -12 + 8 is -4, divided by 2 is -2. Okay? Does that make sense now? Okay. Question? Same question? Great. Other questions? Yes?
Does it make more sense if we calculate all of the values, like BCA, 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 and do an average something? Does it make more sense?
Does what make more sense?
Just calculate all kinds of outputs and do an average of it.
Calculate all kinds of outputs. What do you mean by kinds of outputs?
Does it make sense if we go BCA rather than BCA?
Oh, you're saying like look at the whole trajectory? Well, I mean, we want to look at the reward that we're going to get for the whole trajectory, but because this value function has the shape like it's v of s, the way that we usually think about values is we need to have the value of a specific state. It's not like the value of a whole trajectory, right? So we just want one number for each state. You could also think about the value of a trajectory. If states are Markov, you don't really need to do that because the state will tell you kind of everything you need to know. So you don't need to look at these whole histories. But you might actually do that if you had like a partially observable MDP, like a POMDP. So yeah, I mean, that's a totally reasonable thing to do. Okay. Yes, question.
If we train the model infinite time, then do we can say 3D and 3D have converges in state?
If we train the model for an infinite time, can we say that which converge? Which ones? Would we see that B and E eventually get the same value? Is that the question? Yeah, that's a good question. So hold that thought, and we'll talk about that in 1 second. Yeah, so let me just make sure that like this is making sense to folks, right? Like so how would we calculate the value of C? Who can tell me how we would calculate the value of C? Yeah. We would just use all the episodes, but we would start from C instead of from B or E. Yeah, exactly. So which episodes have C in them? Well, they all do. So we start here. Here, let me clear this out. Okay, this is a little risky. We'll clear it all out. This was a +8. This was a -2. Okay, so now we have to select all the episodes that have a C in them. Here's a C. Here's a C. Here's a C. Here's a C. So we're adding up. What are we adding up? The values from C till the end. Yeah, so the reward values like -1 plus 10. That looks like a +9 in total. -1 plus 10. That's a +9. -1 plus 10 plus 9. -1 minus 10 minus 11. Okay, so we add these all up. Right? We get 9, 9, 9, and -11. And so if we add those all up, we get 27 minus 11 equals 16. And then we have to say, what's the average, right? Divide that by 4, so we should get +4 here. Okay? So if I did everything right, we can erase this and fill in the values. And okay, it's +8, -2, +4. And then for those other two, it's just the value of that state. Okay. Is that making sense to everyone? So really what we're doing is we're just saying like, let's observe some experiences that start in each state and see what value we get. Pretty straightforward. That's why it's called direct estimation. Yeah.
Why we didn't use episode 1 and 2 to calculate B? Because we just add together -1, -1, and 10 to calculate B. But if we calculate the same way as we calculate C, we should actually use -1 and -1 divided by 2, which is -1.
Yeah, so the question is why don't we use all the episodes to calculate the value of B? Is that right? Yeah, so not all the episodes have B in them, right? So all we can do when we're doing direct estimation is we say which episodes have B in them, and it's these two episodes. And then these other 2 episodes don't have B in them. So we don't know what happens when we're in state B if we just look at those episodes. So we only have 2 episodes that tell us information about what happens after B. And so we take the 2 episodes that have data on that, and maybe we go and generate more episodes because maybe that's not enough. But of the 4 episodes we have, the only ones that tell us about the value of B are these 2 episodes, at least if we're looking at terms of like direct estimation.
In that case, the only variables we can calculate from these 4 episodes is the variables that appears in this 4 episode.
That's right, yes. So the comment was, if that's true, then the only values that we can calculate using this procedure are the ones that we saw in our episodes. That's absolutely right.
So the only variables we can calculate from these 4 episodes is C.
The only episodes that, or the only values we can calculate from these 4 episodes are C. So there I would differ with you. So C appears in every episode, but B appears in 2 episodes, and we still have 2 useful episodes we can get data from for B.
But we didn't even use it. As we draw conclusion of A.
Well, we looked at these 2 episodes. We said B appears here, B appears here. This one gives us a +8. This one gives us a +8. Average those together, we get a +8. Okay? Okay, so let's move on. If it's still not making sense, please come up after and we can chat more. So we estimate all these values, right? So this is a very sort of like straightforward approach. We don't have to, use any knowledge of T or any knowledge of R. And in the limit of infinite data, it will converge to the right answer. But someone noticed, hey, why is it the case that B and E have different values, right? B has a +8, E has a -2. They're both going to state C all the time, at least in the data that we have. So that's kind of weird. It feels like there should be some way to pull this information about C into the 2 states that we are sort of reaching C from. Like B and E both go to the same state. So can we use this information and sort of spread it across these other states? So this direct estimation, it will work eventually. It will work if we give it enough data, but it ignores information about state connections. So B goes to C, E goes to C, but somehow they have different values, and that feels a little unsatisfying. And each state must be learned separately, so we have to gather the data and then wait until we have the experiences for it. Okay, so this is where we'll sort of introduce the idea of like, how could we do a little bit better, right? So can we learn from every piece of experience rather than wasting the information that we learned on only the E trajectories and not updating the B trajectories, even though they all go through C? Can we do better than that? Okay. So here's one way that we could potentially try to do that. We're still going to do a fixed policy. We're still doing evaluation, but we're going to move the values towards whichever state we end up seeing. So we're going to essentially do like an expectimax search. So normally this would involve like, let me make sure I have the pen. Yeah, so normally this step would involve a model, right? We have to have a probability distribution over all these outcomes so that we can evaluate the chance node. But now we're just going to say, let's try pulling a sample from this particular state. We take a state, we take an action, and then we see what happens, and it was this outcome. And we'll just say whatever the value of that outcome was will be representative of what we would have got if we had done this whole expectation. So we generate a bunch of data. Sometimes we get this state, sometimes we get that state. But hopefully overall, as we average these things together, we're going to start to get a better picture of what the model would have told us if we knew what the model was. Okay. So we, instead of getting this sum, right? So normally we can write down the sum over all the next states of the transition function times R of that transition plus gamma of V of S prime, right? This is like the way you would do sort of expectation over that chance node. Okay, but now what we're going to do is we're just going to say, we're going to sample this instead. So we're not going to worry about this piece on the left. We're just going to take a sample of this piece on the right. And when we get enough samples, hopefully this thing will look like the expectation we were trying to calculate. So this is the difference between the model-based approach and the model-free approach, right? So this is, you know, imagine we're estimating ages here, right? And on the left, we were estimating a model of the ages. We had this P of A thing. That's like the transition function. And on the right, we were just saying, you know, let's ask a bunch of people, add up all their ages, and divide by the number of people. That's the model-free approach. That's what we're going to do now. And we're going to see how that goes. Okay? Okay, so then we're going to update this value function according to a weighted combination of the previous value of that value function and whatever this sample was. So we're going to move in the direction of this target, and the target is like the value that our sample told us we would have got. So there's a couple ways to write that. We'll get to the details later. But you can view this temporal difference learning. The reason it's called temporal difference learning is we're saying take the difference in time of one value estimate and another. So temporal means time. And this is saying the difference in value between what we thought we were going to get when we look at state S, that's this piece, V of S, and what we actually got when we take an action A equals this policy action, and then the environment responds. And so now we have this sample, this sort of more accurate value sample. And so we're saying, what's the difference between my expected value before I did this transition and my resulting value when I saw the transition? So that's the temporal difference piece. Okay, so TD, temporal difference, is like an approximate Bellman update. If we have a fixed policy, this is like the Bellman update that we saw in the MDP slides. So we have some value function. We're going to estimate that as an expectation over this transition function of this return. This is like the reward for one immediate step plus the gamma discounted next state value. Remember this? So now that's like we have this model in our heads of like how the grid world works. And we're just going to use samples to estimate this expectation instead. So we get a bunch of samples, we run around under this policy in the environment, we accumulate these samples, and for each sample we're going to say write down whatever that reward value was, check our value function for that next state, add these two things together, do the discounting with gamma, and then we're going to sort of add them up and divide by the number of samples. Okay, so we're going to actually run around in the environment. We're not going to we're not going to do this modeling piece anymore. And we're just going to say, I'm going to try this action, and then I'm going to try this action again, and then I'm going to try that action. Maybe I go over here. Maybe I try this action again. Just going to sample some actions under my policy, and then these are sort of like the samples I generate, and we're going to see what happens. Okay. So that's the first idea. Yeah, there's a question. Does that mean it goes back to the original state every time? Yeah, so that's a great point. So if we're trying to estimate the value of the state, we need a bunch of samples from that state, and we might have to return to that state. Yeah. So hopefully we're going to be able to do this in a way where that's not going to be where we're not going to require that. Especially if we have an infinite state space, we're never going to return to the same state. So this should still work in that case, hopefully. Right, so there's a second key piece here, which is that we're going to want to update the value of S after each transition. So if we look at this data set, right, there's this V is like part of how we estimate these samples of what V is ultimately going to become, right? It's very recursive in this sense. Right, we have a value function we're trying to estimate. How are we estimating that value function? We're gathering a bunch of samples. What does each sample say? It says add the immediate reward to our current estimate of the value function at the next state. But our value function is wrong. Like we haven't learned it yet. So most of these samples are going to have like a not super accurate value function. And so it would be really helpful if we could get like some of these samples to be like pretty decent estimates of the value function. Let's say we have a lot of samples, like n is like 1,000,000 samples. Well, the 1,000,000th sample is still using our crappy initial value estimate from the very beginning, because we still haven't updated this value yet. So the idea here is like, what if we update the value after every sample so that our samples get better over time? We're always sort of moving towards this value function. Okay, so we try this thing out, we end up in a state, and then we say, cool, let's do an update, right? Let's update the value of this state based on the reward for going up, which could be like, I don't know, minus 0.1, and then the value of being in this state, which could be, I don't know, whatever our value function says it is. We have some estimate, right? Then we're in this state. I'll clear it out. We take another action, we end up in another state, we do another update, right? We're going to now update the value for this state according to this reward plus this value. And we keep doing this, right? So we then take another action, we end up in this final state, we're going to do a third update, and so on. So like every time we do an update, if we go back to this data set, we have all these examples, but like the reward function or the value function is going to get more and more accurate as we go through these samples, because now we're updating every single time. So that's the second piece. Okay, there's a third piece, which I'll cover briefly, and then we'll have to return to it next time. But there's this idea of a running average. Who's heard of a running average before? This is not like I'm an average runner. This is like, okay, yeah, so this is like, let's say that you want to compute the average of a couple of numbers, like 1, 4, 7, right? How do you do it? It's easy, you add up all the numbers, you divide by n, right? But let's say you have a lot of numbers. Let's say you have 1,000,000 numbers, and there's more numbers streaming in every second, right? And you want to do this really quickly so that you can keep up with all these numbers that are coming in. So is there a way that you could estimate an average in constant time for every additional number? That's what this concept of a running average is. Does anyone know how to do that? Someone does, okay. Yeah, so, right, so you keep track of the number that you've seen, the count, and you keep track of the sum of all the numbers, right? And so if my count is, let's say I've looked at these two numbers, right? So my sum is 5, my count is 2, right? Then a new number comes in, 7 comes in, and what do? We can update the sum by adding 7 plus 7. We get 12. We update the count by adding 1, because there's just one more number, 3. We divide one by the other, and we get our new average, right? So as long as we keep track of a sum and a count, or another way to do it is we can keep track of an average and a count. There's two ways you can do this. You can keep a running average. And so this idea of a running average, we'll come back to this next time. That will be the third idea that's going to make TD work really well for us. So we'll come back to that next time.